one more action that I promised you to talk about. That is the action of the modular group PSL2Z acts on the upper half plane, which is a complex one-dimensional manifold. And this action obviously preserves the complex structure. And moreover, it respects the hyperbolic metric, the Poincare metric at the same time. So there is a very nice picture concerning this. We can draw a fundamental region for this action. So we have circles here. And we have this region here. This is 1 plus E squared, 1 plus E squared of 3 over 2. This is 1 minus E minus 1, plus I think 2. And this is precisely the point I. And a fundamental region for this action is this region. I think that most of you knows about this action. What is new, in which I'm going to talk about, is that if you consider this interval, so there are two fixed points of this action. First, the complex number I. It is a fixed point, it is fixed by the element S. And the point 1 plus I squared I squared of 3 over 2, which is fixed by the element I. Of course, any element in the orbit, in the PSL2Z orbit of these 2 points are also fixed. So there are infinite many fixed points. So if I now take the boundary, take an arc in the boundary of the fundamental region, and if I take its orbit under the PSL2Z action, I obtain a complex and hyperbolic model for the Ferry tree. So the tree goes on like this. Hence, our 3F embeds. Perhaps I must note these two facts. This action preserves and respects at the same time complex structure and hyperbolic Poincare metric. So since this is a geodesic arc, our 3F embeds in the upper half plane as a PSL2Z invariant, not pointwise invariant, but setwise invariant subset, which is a union of geodesic arcs. Well, at the same time, they are real analytic arcs and geodesic arcs. So what does this tell us from our point of view is the following. If I have some free subgroup in the modular group, PSL2Z, then this torsion-free subgroup will also act on the upper half plane, and I can consider the quotient space. So the quotient space is a Riemann surface. The quotient surface is a Riemann surface with a canonical Poincare hyperbolic metric on it, and with an embedded graph f over, no, I have to put the other way around, f over gamma included in h over gamma by geodesic arcs. So in my lecture from yesterday, I told you that any such graph embeds in a topological surface, but in fact we can do much more, and in a much nice manner. We can embed each such graph inside the Riemann surface such that every edge of the graph is a geodesic segment. So, well, I said that gamma must be torsion-free, but we can extend this if we admit the objects called orbifolds. We can admit this, we can extend this extension. Well, we can extend this correspondence to subgroups with torsion as well. In that case, what is the largest subgroup with torsion? It is the PSL2Z. So if if we consider H over PSL2Z, the quotient space will be obtained as follows. So the PSL2Z action identifies this edge with this edge and this segment with this segment, so that the quotient surface will look like this. So there are going to be two orbifold points here. One so the angle here is 90 degrees, and here it is pi over 3 degrees. So this is an orbifold point of order 3, and this is an orbifold point of order 2. So this is something like this. This side goes to infinity. This object is called the modular curve. The modular curve. This is something that you can encounter often also when you are doing geometry as well. For example, there are many questions about the geodesics. For example, I mean, when you have some geodesic here, you obtain some geodesic here, which may do some interesting things. It may be closed, or it may wander off to infinity, and you can ask many questions, and many other apparently independent questions can be studied in terms of these geodesics. For example, there is a famous Markov conjecture, which is a formulation in terms of such the geodesics. Perhaps not on the surface, but on a finite cover of the surface. And we can also ask if, given a geodesic, if its image, for example, on the hyperbolic, on the modular curve is dense, for example. So there are many such questions. And this is a very interesting geometrical object. And we see that our modular interval is embedding in the simplest case, because I have here f over gamma, which is PSL2Z, which, as I told you from my previous lecture, it is just a modular interval like this. So this modular interval embeds inside here as a geodesic arc, which is this arc. So this is the simplest instance of this embedding. Now we can give a panorama of all coverings of the modular interval. I'm going to formulate that in terms of graphs, and every now and then I'm going to mention also the corresponding surface. So at the very bottom, I have this modular interval. As I told you, any graph, any modular graph can be considered as a covering of the modular interval in the orbifold sense. For example, the simplest graph that you can draw after this one is this one. So this one lives on a surface which is sphere. So sphere, I'm going to write P1 over the complex number. So this is for me to call the sphere with 2 orbifold points. So this orbifold point is of order z over 3z, and this is of order z over 3z. And as I told you, there's a covering map between this and this. How this map is defined? So this point you send here, and this point is sent here, 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 this is here, this is here, etc. So whenever I draw such a graph, you can define a covering map in the orbifold sense between this and this. And okay, so the next complicated thing is this one. So this is a degree 2 cover. So this corresponds to a subgroup inside gamma PSL 2Z, which is of index 2. So this is really close to the modular group. And this is also a subgroup of index 2 is necessarily normal, and we can see the Z over 2Z action. So Z over 2 action just exchange these points. You see there's a Z over Z action on this figure, and the quotient is just this one. Similarly, I have this graph. Here, I have 3 orbifold points, order 2, both of order 2. And what else? So this is also normal because there is a group action by Z over 3Z which exchange these branches, and the quotient space is this. So this is also normal, and this is of index. This is an index 3 subgroup inside the modular group. So now we are learning more and more things about the subgroup structure of the modular group. Let us continue. I think this is a very nice game. So we can take a cover of this one, also from my previous lecture. So this space, this space is a quotient of this space under a Z over 3Z action, which just exchange these leaves. So I have Z over 3Z. So this is an index. This is a covering of degree 3. And what else? Since this is a covering of degree 3, this is a covering of degree 2. This is a covering of degree 6. And since there are 6 edges inside the graph, because of the same reason, this corresponds to a subgroup of degree of index 6. As I told you, this is a normal cover of this. This is a normal Galois cover of this, but this is not a Galois cover of this. Because there is no Z over, obviously there is no Z over 6Z action on this figure. However, we can define situations where there is a Z over 6Z action. So this surface, this figure also lies on, by the way, P1 on the sphere, this time with 3 orbifold points of weight 3 each. So the orbifold index is 3 in each case. However, in this figure, I have no orbifold points. In fact, this is, as I also mentioned in one of my previous lectures, is a quotient of the fairy tree by a torsion-free, by a free action. So the subgroup, there is a exact sequence, 1, gamma, PSL 2, Z, symmetric group of degree on 3 letters. And the kernel, gamma, acts freely. It has no torsion points. So here, there are no orbifold points, and this is a very nice and if you don't admit orbifolds, it is perfectly admissible topological space from the topological point of view. This lives on a surface with pi 1 minus 3 punctures. So I can describe them as 0, 1, infinity. In fact, I should have added in each case 1 puncture at infinity. So let me correct this, pi 1 minus infinity. And this is pi 1 minus the point at infinity with 3 orbifold points. Here, this is just pi 1 minus 0, 1, infinity. And the surface, the corresponding surface is just the upper half plane modulo this group action, gamma. And okay, at this point, we get into contact with what is called the dessin. Probably some of you heard about those combinatorial objects, dessin d'enfant of Grothendieck. Now, let us concentrate on this, or let us simplify that figure further. Just consider this graph drawn on the sphere with 3 punctures, 1 at infinity and 2 punctures here. So whenever I have a covering of this topological space, right, I can lift this graph to that topological space. So let's say that I have the topological space is really simple. P1 minus 0, 1, infinity, and let's consider some Riemann surface, which is a covering of this one. So if we and if then I can consider the graph phi minus 1 G. So this is just the graph embedded in the Riemann surface with an extra structure which is a ribbon structure of cyclic ordering of these vertices, these edges emanating from the vertex. So in fact, this graph contains, this abstract graph contains enough information to describe the covering itself. So this way, we can describe all coverings of the thrice punctured sphere. And these account for, and what are these? These are kind of graphs which are similar to one I described. But it's slightly more complicated from my point of view. So this is what is called the dessin. And they are in one-to-one correspondence with the coverings of pi 1, 0, 1, infinity. And if you concentrate on finite coverings only, then these can be considered as branched covers of the thrice punctured plane, which are branched at 0, 1, and infinity. So for me, this summarizes the descent story, but perhaps I have to add a few more things. Yeah, about the arithmetic. So there are some surfaces, some Riemann surfaces, which can be defined over an algebraic number field, and those which cannot be defined over an algebraic number field. And there is a theorem of Belyi, which says that you can define, for example, in some projective space, you can take several equations to describe one-dimensional complex submanifold, so that it is a Riemann surface, And if those polynomials, I mean those equations, polynomial equations are all defined over Q bar, that is to say, if all of the coefficients are algebraic numbers, then this is called an algebraic Riemann surface. And Bellew proved that if you have such an algebraic arithmetic Riemann surface, then it is a covering of this. So it appears here. It appears as a covering of this. And vice versa, any cover of this it can be defined over an algebraic number field. So it is an arithmetic Riemann surface. So Grothendieck, so since these objects are all defined over Q bar, over the Galois closure of the field of rationals, the absolute Galois group of the field of rationals acts on these objects. And he tried to deduce some information from this action. So what does the Galois action do? It sends R to another surface, R prime, which is also a covering of this one. The Galois action doesn't modify the covering structure, the topological structure, mostly. So I obtain another Riemann surface, which is also a covering of this one. So I have an action of the absolute Galois group on these objects, on these coverings, and the question is to get some information about the absolute Galois group this way. He failed. I think that this is a failed project, mostly. Because from computational point of view, it is very hard to describe these as arithmetic surfaces, these covering as arithmetic maps between arithmetic surfaces, and so on. So this project requires some hard computations, and it really goes wild quickly. If you consider some covering of degree 15, you end up with equations, very complicated equations and so on. So it is not obvious how to deduce some meaningful information out of this action. So I think that it is a failed project, but anyway, it is very nice. This is a very nice theorem. And from our point of view, since covering of a covering is a covering, that surface R also appears here as a covering, okay? So when I lift this graph to that surface, I obtain a graph, and that graph defines me another graph, G, which defines the surface R. So we can consider descents as a special cases of modular graphs. So a descent special kind of modular graph. Okay, so here we have the thrice punctured sphere, and I think, if I'm not mistaken, there must be both an arrow here and an arrow here. I don't want to spend too much time on this, but this is a covering of this. Not this. And this at the same time, I think. I'm not very sure. And there's another degree 6 covering, which lives on a torus. I want to draw this on a torus because, you see, I have to give the ordering of edges emanating from each vertex, and it is not easy to do it on the plane. So if we draw it on the torus, then it will be easier, automatic. So something like this. Of course, I have mid vertices like this, and there's a puncture here. So this thing lies on a torus with one puncture, lives on a torus with one puncture, and probably there are some arrows here and arrows there also. I'm not sure, but surely there's an arrow here, and of course surely there's an arrow here. Everything is a covering of this one. If we go on like this on this level, this is what is called the cosite. excuse me, not cosine, just side, or étal side. In a more fancy language, étal side of the modular curve, which consists of all finite degree covers of the modular interval, which is equivalently the set of all finite index subgroups in PSL2Z. Of course, in order to make them correspond to finite subgroups, to subgroups, I must specify base edge in this case. For example, here the base edge could be this, and here the base edge could be this, etc. And you know how, given a base edge now, how to write down the corresponding subgroup of PSL2Z precisely. We all know how to. We just, for example, this is just generated by L and SLS, because I turn once here, and here I do S, L, and S, etc. So this is the subgroup generated by these two elements. And there are many, of course, there are infinitely many such covers, and this is the playground of, and some part of this étal site, which is a kind of category also under the covering maps. This is a playground for much arithmetic, because somewhere here we have the modular congruent subgroups. So what is a congruent subgroup? I'm going to define the simplest of those. There are many variations of this, but we have the reduction map from PSL to Z over NZ, which is surjective. So for any integer n, etc. And the kernel, well, perhaps I shouldn't write. And the kernel gamma and is the principal, if I am right, if I remember that right, principal congruence subgroup of level n. So it is possible to the order of this thing, which will be quite large, something like n to the power 2, something like n to the power 2, perhaps bigger, I don't know. So if n is, I don't know, 5, it's going to have 25 or even more elements. And there is going to be a corresponding graph with as many edges. However, it is not easy. So these are arithmetically defined subgroups. So these are arithmetically defined subgroups of PSL2, which are also, of course, at the same time, which can be also combinatorially defined. However, it is not easy to describe those graphs combinatorially, those combinatorial graphs in an explicit manner. So it's a complicated job. You cannot draw it, but you can. We know the simplest one, this one corresponds to the principal subgroup of level 2. That we know. Yes, I think this, either this or this, but probably this one. Yeah, that one. So the other congruent subgroups are going to yield so complicated graphs. So in the theory of modular forms and functions, these subgroups are really important, and there is really much work dedicated to them. And one thing that you must do when you want to attack such groups is to find some generators of the subgroup. And finding the generators of the subgroup is same as determining its modular graph. And what else? So in general case, I'm going to have Riemann surfaces with some punctures and with embedded graphs such that the complement is a union of punctured disks only. Now I want to go higher. So this is only the finite or étale side, but we can want to go higher. And well, let me again stress that what we are doing is here, from the topological point of view, is really something very easy and trivial. There's nothing complicated about this. We just have one simple tree. We have the subgroup of, we have its group of automorphisms. So not just tree, but tree with its ribbon structure. Its group of automorphisms of PSL to Z. And we consider quotients of gamma by quotients of F by subgroups of that group of automorphisms. So from the topological point of view, this is really something evident. All you need is to be a little patient and describe all those coverings and how they look like. And let us go higher. So these are only finite covers. What can be an infinite cover? So here I'm continuing from here. This is the étale side. So étale side that terminology comes from algebraic geometry. And I have no time to explain that. So in order to define an infinite cover, all it takes is to write down an infinite graph. And we can do such a thing. For example, let us do and continue in all directions. I have to put mid vertices also, of course. And you can do the rest yourself. And there's going to be punctures. And this special graph lives inside pi 1 minus infinitely many punctures. So this is an infinite graph, and we can draw such a thing on something with handles also. Okay, we can imagine that there are handles, and this is some part of this, and handles here, and this can be infinite here, and we may have some other things surrounding handles and so on. So the general picture can be quite complicated. And there are uncountably many such graphs, right? We can draw uncountably many such graphs. That is to say, since each graph is a subgroup of the modular group modular conjugation, this shows that, illustrates very clearly that this group has uncountably many subgroups. And each such subgroup corresponds to such thing. And, well, somewhere here, somewhere in this infinite part, I have this thing. I have things of this form. Something like this here. And I can have, I must have, these vertices must be of degree 3 or 2, so something like this. This is an infinite graph. And its fundamental group is easily seen to be a free product of z over 2z with z over 3z. This is a general fact. If you have such a thing with 3 orbifold points, then the fundamental group of this is going to be a free product of z over 3z, z over 3z, z over 3z. Here it will be, again, z over 3z, z over 3z. Here, there are no orbifold points. It will be z. Z star z. I mean, z free product with z and so on. But if you are in the plane and if you have no loops, then the fundamental group of the corresponding surface, orbifold surface, is going to be a free product of this type. So this graph describes us for each edge. For example, let us fix each edge. This edge, for each edge, this describes me a subgroup of the modular group which is isomorphic to itself. But this is also, in fact, very easy if we look at this problem from another point of view. So here I have, if we compute this fundamental group, I'm going to have some loop, something like S, L, S, and another loop, which and turns back. So this is going to be generated by something like S, L, S, and X, S, X to the power minus 1. Well, if you, so this is a subgroup of the modular group which is generated by an element of order 3 and an element of order 2. And this is going to be isomorphic to z over 2z, 2z, free product z over 3z. Since there are no relations, I think that it follows from Olga's lectures also, that if you have such a subgroup, then it is isomorphic to the free product of the corresponding subgroups. And so I think that from that point of view, it is really easy to understand. For example, okay, let us do this again. If I have the subgroup S and L, which is generated by S and L, then this is the group PSL2Z itself. Instead, if I have a subgroup generated by X, L, X to the minus 1, then I'm going to obtain a subgroup which is also isomorphic to this one, so which is isomorphic to this one, but which is a proper subgroup. And this is that subgroup. What happens if you exchange, this also I explained in my previous lectures, what happens if you exchange the base edge? For example, if this is I and this is I prime, then you just conjugate the following thing, in this case by SL. So this is going to be a conjugation LS minus 1 or something like that. So if I change the base edge, I obtain a subgroup which is conjugate to the first one. So, in fact, I should have drawn this above, but okay, let's do that. So, in this, there is this, I want to erase this because this is not really, I did it a little earlier than I should. So here there is some wild zone, wild territory of uncountable many subgroups. However, inside this, if I again concentrate on this figure is something very regular. And I can draw this figure by a rule, okay, by specifying a rule, and a way to define what a rule is to use Turing machines. For example, here I have some family of subgroups which can be defined by a Turing machine. I mean computable subgroups. Besides that, there are subgroups just like the real numbers. So there are uncountable many real numbers. There are some nice real numbers that we can compute by a Turing machine. And there are those real numbers if you admit that you can never put your finger on it because it is uncountable. And well, and there is a smaller family of subgroups which can be called automatic subgroups. And these are much more simpler Turing machines that can specify much simpler rules. And I just would like to stress that although this is a wild territory of uncountable groups, inside there are some nice subgroups which can be defined via automata or via Turing machines or some intermediary computational model, which might be interesting from several points of view. For example, we must not forget that even though, as I noted here, from the topological point of view, what I'm doing is something really easy. It just takes to spend your time on it to describe this panorama of all coverings of the modular curve or all subgroups of the modular group. There are other points of view on this subject. For example, you may want to consider them, these surfaces, from the point of view of complex function theory. And you may be interested in such surfaces from the point of view of, I don't know, potential theory, things like that. And personally, I am interested in such objects because they let me define some spatial subgroups. Such groups helps me to define some spatial subgroups of the mapping class groups. If I had time, I really would like to express how mapping class groups are obtained in a certain way from these categories. So each of, each of surfaces, such surfaces gives rise to this, of course, mapping class group, and those mapping class groups can be defined in very concrete combinatorial language by using these graphs. So if we leave the this white zone, there is what I call the état cosine. So this is the état cosine of the modular curve, or you can say of the modular interval, which is equivalently, well, let me write this here, the system of subgroups finitely generated subgroups of finite index, of infinite index. In PSL2Z. So, as you notice, these are all, since the graphs are finite, these all correspond to finite index subgroups of the modular group. And these groups are necessarily finitely generated. However, there are some other subgroups which are finitely generated, but not of finite index. For example, the simplest case of such a group is the trivial group. If you quotient the Fairy tree by the trivial subgroup, we obtain, of course, F itself. But what next? So here I have F on top. So this figure is continuing like this, right? So F, the Fairy tree itself, is a covering of this thing and covering of everything that we have here. And I told you how to describe F as a covering in each case. You just cut through here, you take infinitely many copies of this, and you glue them to each other. If you do that, you are going to necessarily end up with a tree. And, well, what is the simplest finitely generated subgroup of finite index in PSL2 after the trivial subgroup? It is, of course, Z over 2Z. So that is to say, for example, we divide F with the action of S. I think I can erase this part now. So what do we obtain when we divide this tree by a subgroup of order 2? If the subgroup is generated by S, then what does it do? As we have seen, it just rotates this around, the tree around this vertex by 180 degrees, like this. So the quotient, if we quotient this by Z over 2Z, then I'm going to have tree like this, etc. And this thing lives on a disk, which I denote by delta. So this lives on a disk delta with an orbifold point. With an orbifold point of degree 2. So this lives inside the disk. You must imagine that. And if you do the same thing, well, what is it? So this, as I told you, lives on the upper half plane. And if you quotient the upper half plane by the action of S, then you just get the half plane, which is from a conformal point of view, which is just the disk. So perhaps I should have said this lives on a half plane, no, quarter plane, yeah. So this is conformally a disk with an orbifold point. So, and the next thing that I have to write here is F over 3Z. And in that case, the situation is similar. That time, this time, instead of rotating around this vertex, the automorphism rotates this around this vertex like this. And the quotient space is going to be this. This again lives on a conformal disk with an orbifold point of order 3. Well, these are finite. These subgroups are themselves finite, and the simplest infinite and finitely generated subgroup of infinite index Z, F over Z. What happens when we quotient this tree with the action of Z? Such a subgroup is necessarily generated by one element, right? So there are two possibilities. Let's say that F over Z equals F over some subgroup generated by X. If X is parabolic, then the subgroup is, the corresponding graph is going to be something like this, with all vertices going outwards and infinite three components. And again, why this is a Z cover of, Z quotient of F, because F is a Z cover of this. And how can we see that? We just split this here, for example. We flatten this out. We see it like this, all vertices are one direction. And we take infinitely many copies of this and glue them one on the end of the other. And the object that I obtained this way is a tree. So the universal cover of this thing is a tree. So this is a quotient of this. And since its fundamental group is obviously Z, it is a Z quotient. What else? If X is hyperbolic, then the corresponding object will have both inner and outer infinite branches, like this. These will be all infinite branches towards inside and outside. So let me stress that the fundamental group of this is Z, which is generated by just one parabolic element. And here it is also Z and generated by a hyperbolic element. And under these ones, I have still many subgroups which are interesting from many points of view. For example, I may have something like this. In general. So I don't have enough space to draw this here, but a general thing that I can have could appear like this. So perhaps some handles, and perhaps some punctures, and some graph. Let me draw something. And some disks, some removed. And inside, of course, I'm going to have some trivalent graph. Of course, you have to put vertices, mid-vertices everywhere. These are not all vertices, but you must not forget these ones, because this is a bipartite graph. And I think that most interesting among this is the case where there are no punctures at all. It is possible that there are no punctures. For example, if I have just a pair of pants, then I can draw here a graph like this. And the corresponding surface on which this lives will be conformally disk minus a disk, right? Minus two disks. By the way, I forget to say something. So this had two subcases, one parabolic case. In the parabolic case, the ambient surface is the punctured torus, punctured disk, or if X is hyperbolic, it is annulus. And as I told you, these objects are especially important for me, more than these ones, from the point of view of mapping class groups, because there is a way to define the mapping class group of each such graph, not of surface, but of the graph. And that mapping class group turns out to be a mixture of the usual mapping class group and a Thompson group, which is also quite important group from group theory. So this is all I want to say for today. Thank you very much for your patience.